Okay, welcome to our lesson on the vector and parametric equations of planes, and then in R3 obviously, because you can't have a plane in R2. Well, we have one plane in R2. R2 is itself a plane, but we're looking at general planes in R3. So before we go into that, let's just recall our vector equation of a line. So vector equation of a line. So vector equation of a line. That was R, and then we could be talking about R2 or R3. No, usually we use A1. So A1, A2, A3. So it was a point plus t times a direction vector. Where t was a real number. Okay, so it was a vector equation of a line in R3. So what that meant, drawing it, your point, I'll just kind of draw it in R2, but whatever. What that meant was A1, A2, A3 was a point, and then your direction vector. So let's say our direction vector was here, so this was M1, and if you repositioned it up at this point, so that would be M1, and then the t kind of moved you along the line, so kind of moved along different values of t, and then you got the all the points on the line. Okay, so one thing we need to talk about is if you remember what a spanning set was, or the span of a set of vectors. So spanning set was the set of all linear combinations of a set of vectors. Okay, so let's say for example your set, the vectors you're looking at, is just one vector, or in this case M. So what is a span of M? So just this one vector. Well, that's just all multiples t of M, t times M. Okay, so if M is this, then the span of M is all multiples, which is just the line. Right? So, and that's really related to how we get the equation of a line. It's just the span of the direction vector, and then you have to add a vector to get you up to the correct position of the line if it doesn't go through the origin. So the equation of line comes from the span of just a single vector. So a single vector will span a line. But now what happens when we're talking about planes? We did talk about this before when we talked about spanning sets, that a plane is spanned by any two non-collinear vectors on that plane. Okay, so let's just talk about what that means. Okay, so let's say you have a plane. It's supposed to be a plane and it's infinite. I drew the edges, but really it goes on forever. And then you have two vectors on that plane. So this vector u and this vector v are both vectors on the plane. So u and v are vectors on a plane. I'll give the plane a name. I'm going to call it, when we do planes, remember we use R for lines in R1. We use a pi for plane. On plane pi 1. Okay, so this is the plane pi 1. Okay, so what that means is any point, right? Let's say this is the origin, right? Because u and v positioned at the origin. Let's use a different color here. So let's say any point, this point here, I can get to by doing a linear combination by basically adding multiples of u and v, right? All I have to do is, it looks like, in order to get this vector, all I have to do is add a little bit to u and then travel along in the direction of v. Maybe add a multiple of v. Right, to get to, and any point I could put on the plane, right, down here, just add a multiple of u, a multiple of v, and then that parallelogram would be formed. So any point on the plane I can get to by adding a multiple of u and v. So that's what that means. So let's just write that down. So any point on plane, or any vector on the plane, will be equal to some multiples of u and v. So the letters I'm going to use here, I'm going to say s times u plus t times v for some s and t, right? Depending on the point, you have to use different s's and t's, which are real numbers. Okay, so that actually looks like, that will generate the plane. The only problem is that would only generate planes that contain the origin, where u and v are positioned at the origin. But the same deal with lines. Remember, when we talked about lines, if we just took multiples of tm, then we'd always be going through the origin. But if you want the line to not be through the origin, you just have to add any point on the line. Well, same thing for the equation of the plane. If the plane is shifted up and not going through the origin, or down, or wherever, you just need to add a starting point. So we'll just write the vector equation. So if we need a point on the line, so a1, or a plane, sorry, is a point on the plane on a plane, and we'll use u and v. So call it u1. And v are two non-collinear vectors on the plane, or in the in the direction of the plane. Then the vector equation is, so here we're going to use pi, which we could say is equal to x, y, z. So the points x, y, z will be equal to, so you need to start with the point a1, a2, A3, so that will get you to the plane, and then you need to add multiples of the kind of direction vectors, or the vectors which are on the plane, and that will move you around the plane to generate all the points. Where t and s are real numbers. Okay, so that's our definition of vector equation. The vector equation is this thing right here. That's the important part. Okay, so it's very similar to the vector equation of a line, except now you need a extra direction vector to move you because the plane is two-dimensional, right? A line is just one-dimensional, so you just need to move in the one direction vector, but now a plane is two-dimensional, so you need to move sort of in two dimensions. And then quickly, the parametric equations. Well, that's the exact same thing as with the vector equations of lines. They're related in the same way. It's just the components. So there's going to be three components now, right? An x component, x will equal a1 plus t times u1 plus s times v1. Y will equal a2 plus t times u2 plus u2 s times v2, sorry, and z will equal a3 plus t times u3, it's not a band, plus s times v3, where t and s are real numbers. Okay, so that's the parametric equations, very similar to before, except now there's that extra direction vector. Okay, so that's our definitions of vector and parametric equations. Next video we'll do some examples.